In the present video, we will find the relation between the modulus of elasticity and the modulus of rigidity. Modulus of elasticity, that is capital E, is the ratio of stress, that is sigma, and the strain, that is epsilon. So capital E equal to sigma divided by epsilon. Similarly, modulus of rigidity, capital G, is the ratio of shear stress, that is small q, and shear strain, that is the phi. So G equal to Q divided by phi. Now we will find the relation between the E and G by considering a square block and subject it to a pure shear. Let consider a square block ABCD of side small a and of thickness is unity, which is perpendicular to the plane of drawing. Let the block is subjected to shear stress of intensity small q as shown in the figure. So in this figure we have to observe that we are considering a square block, that is ABCD, which is subjected to a pure shear small q, and considering the square block side is the small a. Due to these stresses, the block will be subjected to a deformation such that the diagonal AC is elongated and the diagonal BD is shortened. Block ABCD deformed to the position A1, B1, CD through the angle phi relative to the face DC. So let us observe the picture. Block ABCD is deformed to the position A1, B1, CD, and which make the angle phi relative to the face DC when it is subjected to a pure shear. Moreover, diagonal AC length is increased to a A1C. So diagonal AC is elongated. Similarly, another diagonal. So length is the BD, which is the reduced to its length B1D. So diagonal BD is shortened. Let's consider the diagonal AC. Its length is the increased to a A1C, which means initial length is the AC, and after the deformation of the block, final length of the diagonal is the A1C. So increase in the length of the diagonal AC equal to the A1C minus AC. Next we have to draw a line A2, which is perpendicular to the A1C, and here observe the triangle ACA2, which is making the very small angle. So here observe the triangle ACA2, so which is making the very small angle. Then we can be written as the length of the AC, which is equal to the A2C. Now we have to substitute this value in the increase in length of the diagonal AC, that is A1C minus AC, which will become the A1C minus A2C. So here observe the A1C minus A2C, which is equal to the A1 A2. So here observe the A1 A2 is the right angle triangle. So we have to take the A1 A2 right angle triangle. So from this right angle triangle, cos theta equal to the adjacent divided by hypotenuse, that is the cos theta equal to the A1 A2 divided by A1. So from this one, A1 A2, which is equal to the cos theta into A1. So we know that when the increase in length of the diagonal AC equal to the A1C minus A2C. So we know which is equal to the increase in length of the diagonal, which is equal to the A1 A2. So from this right angle triangle, A1 A2 value equal to the A1 into cos theta. So increase in length of the diagonal AC equal to the A1 into cos theta. Next we will determine the cos theta value. For this one I have to considering the right angle triangle BAC. So here BAC is the right angle triangle and the angle between the AC and the AB is equal to the 45 degrees because so inclination of the diagonal in the square block is the 45 degrees. So in the same way we have to considering the right angle triangle A1 and A2. So this is the here A1 A2 also one right angle triangle and the angle between the A1 and A1 A2 is the 45 degrees. So here 45 degrees. Then here cos theta equal to the so which will become the cos of 45. Then increase in length of the diagonal AC will become the A1 cos 45 which is equal to the A1 divided by the root 2. So next we have to discuss about the shear strain when the block is subjected to a pure shear. So for this one we have to considering the right angle triangle A1, A and the D. So from this right angle triangle, so tan phi equal to the transverse displacement divided by distance from the lower face, that is the AA1. So AA1 divided by AD. So we know that one the AD value is the small a. Then tan phi equal to the AA1 divided by small a. So here phi is the very small value, then phi is nearly equal to the tan phi. Then shear strain phi equal to the AA1 divided by A. So this we have to substitute AA1 value in the increase in length of the diagonal AC which is equal to the AA1 divided by root 2. So we know that one the phi equal to the AA1 divided by small a. So from this one AA1 equal to the A phi. Then increase in length of the diagonal AC equal to the A phi divided by root 2. We know the increase in length of the diagonal AC which is equal to the A phi by root 2. Next we determine the strain of the diagonal AC which is equal to the increase in length divided by original length. Here increase in length equal to the A phi by root 2 and original length is the AC. Then strain of the diagonal AC will become the A phi by root 2 into 1 by AC. So next we have to determine the AC value. For this one I have to considering the one right angle triangle here, that is the triangle ACD. So here from the triangle ACD, AC square equal to the AD square plus DC square. Then AC equal to the root of AD square plus DC square. So then strain of the diagonal AC equal to the A phi by root 2 into 1 divided by root of AD square plus DC square. So AD is the length of the side of a square block, that is the small a. Similarly DC value also small a. So AD square will become the small a square and AC square will become the small a square. Then this equation will become the A phi by root 2 into 1 divided by root of A square plus A square which is the 2A square. Then strain in diagonal AC will become the A phi by root 2 into 1 divided by root 2A. So here AA will be cancelled and root 2 into root 2 will become the 2. Then strain of the diagonal AC equal to 5 by 2. Let's consider this is the equation 1. Next we will determine the strain in the length of the diagonal AC in the another way. So for this, consider the diagonal AC, and when the face AB is subjected to shear stress, intensity is the small q, then the element of diagonal AC is subjected to the tensile stresses along the AC and compressive stresses in the opposite direction. So I have to observe in the picture. So here, so tensile stresses are acting along the AC and compressive stresses are acting in the opposite direction. Moreover, these diagonal tensile and compressive stresses values are the same value of the shear stress intensity, that is the small q. Then strain in the length of the diagonal AC equal to the strain in the length of AC due to diagonal tensile stresses on the plane BD plus strain in the length of the AC due to diagonal compressive stresses on the plane AC. So which is nothing but, so strain in the length of the diagonal AC equal to the longitudinal strain plus lateral strain. So I have to determine the longitudinal strain and also lateral strain for the diagonal AC. Then total strain of the diagonal AC equal to the longitudinal strain plus lateral strain. So longitudinal strain is the tensile strain on AC due to tensile stresses on plane BD, and lateral strain is the tensile strain on AC due to compressive stresses on the plane AC. So first we have to calculate the longitudinal strain, that is the, so epsilon equal to the stress divided by Young's modulus, which is equal to the epsilon equal to small q divided by capital E. So next we have to calculate the lateral strain. So we know the Poisson ratio, that is mu r 1 by m. So mu r 1 by m equal to the lateral strain divided by longitudinal strain. So from this one we can be written as lateral strain equal to the 1 by m into longitudinal strain. So we calculated the longitudinal strain, which is equal to the q divided by E. So substitute here, then lateral strain will become the 1 by m into small q divided by capital E. Then total strain in the length of the diagonal AC equal to the longitudinal strain, that is q by E, plus lateral strain, that is the 1 by m into q by E. Then strain in the length of the diagonal AC equal to the q by E into 1 plus 1 by m. Let's consider this is the equation number 2. We determine the strain of the diagonal AC, which is equal to the 5 by 2, and also which is equal to the q by capital E into 1 plus 1 by m. Next we will discuss the modulus of rigidity capital G, which is equal to the shear stress, that is small q, divided by shear strain, that is the phi. Then capital G equal to the small q divided by phi. So next we will find out the relationship between the, so capital E and the capital G. So that is relationship between the modulus of elasticity and the modulus of rigidity. So from the equation 1 and 2, we can be written as phi by 2 equal to q by E into 1 plus 1 by m. So this is, we can be written as phi value as the, so from the modulus of rigidity equation, phi equal to the, so small q divided by capital G. Then q divided by 2g equal to the q by capital E into 1 plus 1 by m. Here small q will get the cancel. Then 1 by 2z equal to the 1 by E into 1 plus 1 by m. So this equation we can be written as E equal to 2g into 1 plus 1 by m. So this is the relationship between the modulus of elasticity capital E and the modulus of rigidity capital G. Thank you.